Then attribute B can also be attached to a grammar symbol as an inherited attribute. So if the attribute is attached to one of the grammar symbols in the alpha part, or on the grammar symbols on the right hand side of the grammar production rule. So if the attribute B is attached to grammar symbols in alpha, and the attributes C1 and C2 up to Cn are attributes of the grammar symbols in the production rule A drives alpha, then we can say the the attribute B is an inherited attribute. Why? Because we can consider the previous example, like that means if, for example, the attribute C2, is C2, if we have a semantic rule which is defined as the attribute B like E2 or E1 is calculated as attribute B dot A, assuming that there is an attribute attached to non-terminal B plus 2, let's say. So as you can see from the production rule, B is the parent. B is the parent having the attribute A, and under B we have here small b as one child, then small a as another child. So if based on the production rule, we can see that the attribute of, we can have like C, we can attach attribute B, attribute E1 to the grammar symbol B. So based on the semantic rule which is associated with the production rule B drives BA, the calculation of the attribute E1 which is attached to the grammar symbol B is computed from the attribute of grammar symbol B, which is the non-terminal, and this non-terminal B is the parent of the grammar symbols B and C. So here, because of this, the value of the attribute E1 is computed from the value of attribute A, which is the attribute of the parent. So it is inherited from the B attribute, which is the parent. So here, because of this, we can say the attribute E1 is an inherited attribute. So we can have such semantic rule associated with the grammar production rule. So here, an attribute in general, an attribute can be synthesized attribute or inherited attribute. And a very important note here that you should keep in your mind is terminal symbols can have only synthesized attributes. Only synthesized attributes. But non-terminals can have both inherited and synthesized attributes. So for a given non-terminal, we can attach inherited attribute, or we can attach synthesized attribute. So let's consider an attributed grammar. Why this grammar is considered as an attributed grammar is because each production rule of the context-free grammar is associated with semantic rule. For example, for the first production rule of the grammar, expression 1 derives expression 2 plus term. The semantic rule that indicates the meaning of this production rule says expression 1 dot val. Here the attribute is val, and here expression 1 dot val is equal to expression 2 dot val plus term dot val. So the attribute val is attached to the grammar symbols, both on the right hand side and on the left hand side. So as you can see, the attribute val value is computed from the children, because here expression 2 and term are expression 2 plus and term are the children of expression 1, because we can, when we are visualizing the relationship between those grammar symbols using tree notation, we can put expression 1 as parent, and under that parent we can specify expression 2 as the first child plus as another child, the second child, and term as the third child. So from this we can say that the attribute val is a synthesized attribute, and here another way of determining that whether the attribute val is synthesized or inherited is just we can have a look at the last production rule, which says factor drives number. Here number is terminal symbol, opening bracket is terminal symbol, closing bracket is terminal symbol, multiplication, addition and subtraction are terminal symbols, and we have this statement: terminal symbols can have only synthesized attributes. So once we identified the terminal symbol, any attribute that is attached to the terminal symbol is a synthesized attribute. So in a simple way we can determine that the attribute val is synthesized attribute. And here another very important point regarding the attributed grammar is the classification, the category of the attributed grammar. So if a given grammar is having all of its attributes as synthesized attributes, then we can classify that grammar, attributed grammar, as S attributed grammar. So if each and every grammar symbol is attached with synthesized attributes. We can say the resultant grammar as S attributed grammar, and if the grammar the grammar symbols are attached with synthesized as well as inherited attributes, then we can say the grammar is L attributed grammar. So from this perspective, we can categorize the given this grammar as S attributed grammar, because the only attribute that is attached to each grammar symbol of the given grammar is val, and val is synthesized attribute. So because of this, we can say that the grammar is S attributed grammar. S attributed grammar. So S attributed definitions is the one that is having only synthesized attributes, and L attributed definitions or L attributed grammar is the one that is having inherited attributes too. So not only synthesized attributes, but in addition to synthesized attributes, they also use inherited attributes. But here the use of inherited attributes is in a restricted fashion. This is very important. So the use of inherited attributes in L attributed definitions is with a restricted fashion. So we will see why and how, what rule or what condition should be met to, or when we are attaching the inherited attributes to grammar symbol. So here, to implement these attributed definitions and the attributed definitions, here the easy. So we can simply evaluate the semantic rules in a single pass during the parsing. So when we are performing the parsing process, the evaluation of the semantic rules is just simply and easily performed during the parsing process. So to implement the implementation of the S attributed definitions are a little bit easier than the implementation of L attributed definitions. So since the S attributed definitions contain only synthesized attributes, their evaluation is just performed simply during the parsing process. But here the L attributed definitions can always be evaluated by debits first, that is from left to right. So from the left to right we can evaluate. That means they can also be evaluated during the parsing. So S attribute definitions can be efficiently implemented. Then so we are looking for the larger S attribute definitions, which is the subset of syntax directed definitions, which can be efficiently evaluated. So when we are attaching inherited attributes to grammar symbols to make the grammar as L attributed grammar, the restriction is, for example, if we have the grammar production rule as A drives x1 x2 up to xn, assume we have this grammar production rule, and we want to attach an inherited attribute to one of the grammar symbols on the right hand side of the production rule. So the inherited attribute depends only on, the first condition is the attributes of the symbol x1 up to xj to the left of x up to xj minus 1 to the left of xj in the production rule, and the inherited attribute of a. So if those two conditions meet, then we can say that the attachment of the inherited attribute is valid, and hence we can say the grammar is L attributed grammar. If not, the grammar will not be considered as L attributed grammar because of the illegal use of attaching the inherited inherited attribute to the grammar symbol. So what does it mean? Oh, to clarify, for example, if we have a requirement of attaching an inherited attribute to grammar symbol x2, so that inherited attribute can be calculated from the attributes of x1, because x1 is to the left of x2. So the inherited attribute of x2 can be calculated from the value of the attribute of x1 and or the inherited attribute of the parent a. If we wrongly defined the semantic rule that calculates the value of inherited attribute of x2 from x3, it is illegal because it is violating the first condition of attaching inherited attribute to given grammar symbol. So this is very important conclusion here. Every S attributed definition is L attributed definition. Every S attributed definition is L attributed definition because L is the largest set and S is a subset. So S is the subset of L because L contains both inherited and synthesized attributes, whereas S contains only synthesized attributes. So because of that, of the two restrictions, we can have such a relationship between the two. So if the two conditions meet for the use of inherited attributes in attaching the grammar attributes to the grammar symbols, if the two conditions meet, then we can say the grammar is L attributed grammar. So let's consider this simple example. Assume we have a grammar having those two production rules: A drives LM, A drives QR. So, and assuming that we have also semantic rules attached to the grammar production rules. For the first production rule, we have the semantic rule, For the second production rule, we have the second semantic rule. So this is an attributed grammar. Because each production rule of the grammar is associated with corresponding semantic rule. So now it is time to decide whether this grammar is L attributed grammar or S attributed grammar. And if it is L attributed, it is an attributed grammar having either both synthesized attributes or both inherited and synthesized attributes, but the inherited attributes are used in a restricted fashion, that is used by keeping the two conditions. So as you can see in the semantic rules of the attributed grammar, L is attached with in attribute in, and there is a function L that takes the parameter as a parameter the attribute value, value of A, which is the value of attribute I. So here from this we can see this L is the child of the non-terminal A. So as this is calculated from the parent, we can say the attribute in is an inherited attribute, and attribute is also calculated from L attribute, which is S. So it is calculated from L, which is to the left side. So as it is from the left side, that is from the same from the sibling, so it is calculation which is from the attribute S. So we can say it is an inherited attribute, and the S attribute, which is also attached to the non-terminal A, is calculated from M attribute, and this M is a child of non-terminal A. So we can say this S is a synthesized attribute because it is calculated from the sibling, that is from the child. So in is an inherited attribute and S is a synthesized attribute. So we should ensure that the inherited attribute in is attached to the grammar symbols in a correct or in a valid way. So this inherited attribute is calculated from A, possible. L attribute, the inherited attribute of L is calculated from the parent, that's possible. The inherited attribute of M is calculated from L to the left side, possible. The synthesized attribute, no need to worry because the attribute of A is calculated from the child, possible. The synthesized attribute, correct. And for the second production rule, the inherited attribute of R is calculated from the parent, correct. The inherited attribute of Q is calculated from there is the function Q, small q, which takes as a parameter the attribute value of R. So R, the synthesized attribute of R, which is calculated from the synthesized attribute of R, and R is the non-terminal R is to the left side, to the right side of Q. So the inherited attribute of Q should not be calculated from the attribute of R, whether it is synthesized or inherited, because when we are computing or calculating the value of the attributes of Q and R, the order is from left to right. So without calculating the value of R, we cannot, without calculating the value of Q, we cannot calculate the value of R. So the value of the attribute R will be calculated after the value of the attribute Q is calculated. So that's why that restriction is impossible. as restriction is applied. So since the second semantic rule part is violating the two conditions, the first condition, this is this shows that the grammar is not a attributed grammar. Although it is an attributed grammar, the grammar is not a attributed grammar. The grammar is not a attributed grammar. Why? Because the grammar contains both inherited and synthesized attributes. Why it is not an attributed grammar? Because it violated the use of inherited attributes. So another concept is dependency graph. And dependency graph is used for showing the dependency between the attributes and enables to find an evaluation order for the semantic rules. So once we define semantic rules to production rules of a given grammar, then we can use dependency graph to show the evaluation order of the semantic rules. So for example, they assume we have such expression, which is the expression 34 minus 3 in bracket then times 42. So this is the expression, which is 34 minus 3 bracket times 42. This is a expression, the mathematical expression, which is represented by this parse tree, based on the grammar which is defined on the previous slide. So we can consider this grammar, the attributed grammar, to construct the parse tree for this expression. So just you can simply follow the leftmost derivation or rightmost derivation in order to construct this parse tree, because parse tree is simply the graphical representation of the derivation process. So once you derive the given input string 34 minus 3 in bracket times 42, then you can convert the derivation process into parse tree. So based on the production rules, you can just derive or draw the parse tree for the expression. Then once you constructed the parse tree, you follow the semantic rules attached or associated semantic rules, those semantic rules to construct or the parse tree. So 34, the number factor derives number, for example, so the first production rule says the factor derives number, which says factor dot val equal number dot val. So number dot val, so val is the attribute, the semantic, which carries the semantic meaning. So this production rule, the semantic rule of this production rule, says that the value of the grammar symbol factor is calculated from the value of the grammar symbol number, and the number value is just given, it is attribute value is computed from the lexical value. So from the given expression, the lexical value of the number grammar symbol, as it is a terminal symbol, that value will be the lexical value. And the given, in the given expression, the first expression, that's the first semantic, the lexical value is 34. So 34 is assigned as a value of the attribute, and this factor value is calculated from the number. So simply assigning the value of the val attribute, the value of the number val attribute. And similarly, the term value is assigned from the factor val attribute. Then expression similarly, just simply following the semantic rules. We can just calculate the attribute values. So similarly, for number we can assign the next lexical value val, then for factor 3, then for term 3. Then for this production rule, which says expression equal expression minus term. So for the production rule, which says expression drives expression 2 minus term, this is the semantic rule. So the value of expression 1, that is just this subscript, is to simply indicate that the grammar symbol expression is the one on the left side, and with the subscript 2 is the one on the right side. But expression, the two grammar symbols are the same. So here the value of the expression on the left side is calculated by reducing the expression on the right hand side by the term val, attribute value. So that's why we can just reduce 34 by 3 and becomes 31. So the val of the attribute val of this expression will have 31. Then factor drive this expression, we have factor drive this expression, so simply we can assign 31 to the val attribute, then the term 31, and next term the number is assigned the lexical value 42. Then for the factor we can assign the number val attribute value. Then finally we have the term, the production rule, term drives term times factor. So based on the semantic rule, we can calculate the value of the term attribute by multiplying 31 with 42, then having this value. So the resultant value, this one. So expression drives term, simply copying the value of term val to expression. So this is the tree having all attributes computed their values. So a tree or simply the parse tree showing attributes with their values is called annotated parse tree or decorated parse tree. So after calculating each attribute value, the resultant tree becomes annotated parse tree or decorated parse tree, and this is an output of the semantic analysis. So when we are calculating the value of each attribute of the grammar symbol in the given grammar, this is in other words the semantic analysis, and the output is the decorated parse tree or the annotated parse tree. So let you consider this one is also another attributed grammar. Is this grammar a attributed grammar? What about this one? How we can just derive? Can we, is this grammar a attributed grammar or S attributed? Let you categorize this grammar. So let you categorize this grammar as L attributed or S attributed grammar. This additional example, and this is based on the given grammar. You can just construct the parse tree for this expression. 5 plus 3 times 4. Just construct the parse tree, then decode it. So this is an annotated parse tree. So calculate the construct the parse tree and annotated parse tree or decorated parse tree for the given expression. And this dependency graph for the annotated parse tree. We can use dependency graph to show the order of evaluation, how the attributes are calculated. Attributes are calculated for each grammar symbol in the parse tree. So the just dependency graph is simply a graph which is used for showing the order of evaluation, of the semantic rules. So you can construct some semantic rules for the given grammars. So you can consider those grammars and construct the semantic rules. So this is also additional example for declaration statement. For declaration statement, you can just consider this attribute. This is a string set of input symbols. Real PQ. Is this statement correct as per the given grammar? This semantic, this attributed grammar. So according to this attributed grammar, is this expression correct? Statement real P space Q. So if this is correct, then we can construct such parse tree. So let you also check for this one is what about int x comma y semicolon. Is this statement correct? This statement correct? Just construct parse tree. Decorated parse tree for this one based on the given attributed grammar. Based on this attributed grammar that you construct. This is also an additional grammar that you think of, and this one is for computing or creating binary numbers. So the second notation is translation schemes. So as we have discussed it, that there are two notations that we can use for associating semantic rules to grammar product rules. So the first one is syntax directed definitions, and the second one is translation scheme. So in syntax directed definition, we will not say anything about the evaluation times of the semantic rules. So when to evaluate, when to calculate the attributes, or how about the order of evaluation. But in some translation scheme, we can associate attributes with grammar symbols and the semantic actions. Here, when we are associating semantic actions or attaching associating semantic, just put the semantic actions between the braces, so we put the semantic actions between braces. So the order of evaluation of the semantic actions will be determined by the location of the semantic actions. So where we place the semantic action between the grammar symbols on the right hand side will determine when to evaluate the semantic action. So for example, if we have a grammar production rule, A drives X, Y, we may put semantic action before X. We can also put semantic action between X and Y, or we can put semantic actions after Y at the right end of the production rule. So this shows that the last production semantic rule will be evaluated at the last. That is, after the previous two semantic actions are evaluated, then lastly the last semantic action will be evaluated, and the middle one will be evaluated after the first semantic action is evaluated. So before without evaluating the first semantic action, we cannot evaluate the middle one. We cannot also evaluate the last semantic action. So their location determines the order of evaluation of the semantic rules. So here the terminology we use in the context of translation scheme is semantic action, not semantic rule. In the case of syntax directed definition, we call them semantic rules, and in the case of translation schemes, we call them semantic actions. So for example, if we have the production rules of a given grammar, it is simple to convert translation syntax directed definitions of S attributed definitions or S attributed type into translation scheme by simply putting the semantic rule at the end of the production rule. So for example, if we have such attributed grammar or S attributed grammar, we can convert this S attributed grammar into translation scheme notation by simply taking the semantic rule as a semantic action by putting the semantic rule within the braces at the end of the production rule. So there is no separation between there is no separating space between the production rule and the semantic actions. So here we just simply put the semantic action at the end of the production rule. So this is the translation scheme representation for S attributed grammar, the translation scheme. So when translation schemes are just added or just defined for a given grammar, we can then evaluate using simple left to right traversal. This is another example that shows the conversion of infix expression to postfix. This is an infix expression, a plus b plus c, and ab plus c plus. This is a postfix expression. So to convert this infix expression to postfix, we can have such translation scheme. This translation scheme notation that can be used for converting infix into postfix. So let's consider this example. For example, here we can just translate convert this infix expression to postfix by simply driving. First we should drive that string a plus b plus c. So we should first drive the string and then construct the parse tree for the derivation process of the string a plus b plus c. So when we are constructing the parse tree, we should place the corresponding semantic rules as a node. So for example, if we use this production rule, r drives plus t, then in brass print plus, then r1. So under r we will add 4 nodes plus t and the semantic action, and finally r1. So the semantic actions are also added as a node under the grammar symbol. So that's why we constructed the tree like this for the expression a plus b plus c. So id for the generation of the given input string a plus b plus c, we have such tree. So e is expanded to t and then r, and t is expanded to id, then the semantic action which prints a, then r is expanded to plus t, then print plus, then r. For t we have expanding id and print b action, then for r we have this one, r expanded to plus, then t, then print plus, then r, and finally this one should be modified. This one should be modified like this. So finally we have id, then print c, then r2 epsilon. So we can just traverse this tree using the Deb's first traversal operation. Then finally we by considering only semantic actions from the tree. So print a, then print b, then print plus, then print c, then print plus. So lastly we will have, by executing only semantic actions from the tree, we will have a postfix expression of the given infix expression. So the infix expression can be easily converted into the postfix expression by simply executing or considering the semantic actions from the parse tree. So this is just the general rule of how we can use inherited attributes in translation scheme, just similar to the way we use inherited attributes in a restricted fashion when we are defining or attaching the inherited attributes in a letter-based grammar. We should also give attention to the use of inherited attributes in translation schemes. So let you consider those rules whenever you are attaching inherited attributes in translation schemes. So that's all. So next we will see type checking.